In this section, we're going to talk about log functions or logarithmic functions, or you could say logarithm functions. But basically, a log function would be in the form of f of x, and you read this where it says log of x base a. And a is actually called the base of the log. X we can call the argument of the log. Now, the base has to be greater than 0 and it cannot equal 1. So it's similar to the base of exponential functions as far as what the values can be. Now, the domain of your log function is all positive real numbers, or all real numbers greater than 0. So some examples of logs would be like, here you have f of x equals the log of x base 3. Here you have f of x equals the log of x base 1.5. And of course you could have a lot of different logs. The key to really understanding what a log represents is to know this exponential and log relationship that I've got here. So let me just show you here. If you have a relationship that says y is equal to the log of x base a, then that is equivalent to saying exactly this. Take the base, raise it to the y, and that's got to equal the argument x. So anytime you have y equal the log of x base a, that's the same as saying a to the y is equal to x. So what you notice here, this y is actually an exponent in this expression, and so that's what's true about logs. Logs are really just represent exponents. So if I were to tell you that this is a true statement, and it is a true statement, that log of 100 base 10 is 2, then that would be the same as saying the base, which is 10, raised to the log, which is 2, equals the argument 100. So that would be the same as saying 10 squared equals 100. And of course you know 10 squared does equal 100. If I were to say that the log of 1/25 base 5 is negative 2, that would be equivalent to saying that 5 to the negative 2 is equal to 1/25. So the first two there, they make sense once you see it in exponential form. The second one is more of an expression. It says the log of s plus t base b equals r. So if I wanted to write that in exponential form, I would take the base b, raise it to what the log equals r, and then it would equal the argument, which is s plus t. So that's how you convert from log to exponential form. Now I can also give you some true statements in exponential form and convert it to log form. So if I say 7 cubed is 343, which is a true statement, then that's the same as saying the log of 343 base 7 is 3. Notice what the log equals. That's equal to the exponent from over here. Okay, and then if I said 1 over 1,000 is 10 to the negative 3, which of course is a true statement, then that would be the same as saying the log of 1 over 1,000 base 10, since that's the base, is equal to the exponent negative 3. And if I said b to the 0 equals 1, that would be the same as saying the log of 1 base b is the exponent, which is 0. Now as far as graphing logs, what you have to do to graph logs is the easiest way. Since this is y, we can say this is y equals log of x base 2. We can actually write this in the form, in an exponential form, and say 2 to the y equals x, or x equals 2 to the y. So this time, in order to set up the table, what I'm going to do is I'm going to pick y values and then plug them in to get the x values. So I'm going to use the y values negative 2 through positive 2 and see what the x value is going to be. Now up here we know x is 2 to the y, so if y is negative 2, x would be 2 to the negative 2, which is 1/4. If y is negative 1, x would be 2 to the negative 1, which is a half. If y is 0, x would be 1, 2 to the 0. and if y is 1, x would be 2 to the first, which is 2, and if y is 2, x would be 2 squared equals 4. So that's how I get these x values in the table. Well, if you go 1/4 -2, that's right here, and then to plot 1/2 -1, that's right here, and then to plot 1, 0, you're here, and then to plot 2, 1, you're here, and then to plot 4, 2, you're here. So you can see that this graph is an increasing graph, and it kind of begins to flatten out the farther you go to the right. Now, similarly, I could graph these values. I'm not going to go through and show you the table, but I will show you what I did. Remember, you can think of this as y equals log of x base a fourth, which would be the same as saying x equals 1/4 to the y. So if I picked x values and plugged them in to get, if I pick y values and then plug them in to get the x values, then I'll get this table. Now, I'm only going to focus on these three values in the middle here because the others go off my chart. But I know that when y is -1, x would be 4, so that the point 4, let's say 4, -1 would be on the graph. Well, that would be way over here, somewhere down here, so that would be 4, -1. It's on my graph. Now 1, 0 would be right here, and then 1/4, 1 would be right here, and then 1/16, 2 would be right here. So I actually kind of fibbed a little bit. I'm actually going to use this one too. But if you look at these 4 points here, then you can see here the graph is decreasing, and it also begins to flatten out as x gets large. This one, y equals log of x base 5, I can write it as x equals 5 to the y, and it's going to look a little bit like the log of x base 2, but notice it's going to flatten out a bit quicker. If you plug values in for y like -2, -1, 0, 1, and 2, you'll get 1/25. So if x is -2, if y is -2, x is going to be very small. And then if y is -1, x is going to be 1/5. And then if y is 0, x is going to be 1. And then when y is 1, x is going to be 5. And you have to go way out here to 25 to get up to where y is 2. So that would be way over here somewhere. So you can see that it flattens out a bit quicker than the log of x base 2 does. Okay, so just like I told you before, if you know how to graph the log of x base 2, then you can graph this. The minus here just flips that log around the x-axis, and then the +2 just shifts it up 2 units. Here, if you know how to graph log of x base a fourth, you can graph this. When you replace x with -x, it just flips it around the y-axis, and then the 3 stretches it by a factor of 3. And then this one, if you know how to graph the log of x base 5, when you replace x with x minus 2, that just shifts it to the right 2 units, and then the 1/3 shrinks it by a factor of 1/3, and then the +3 shifts it up. Obviously, you can graph these on a graphing utility to see that action. Now, the properties of log functions basically say that the domain of your log function is the set of all positive real numbers. So that's, notice that this function never touches, notice it gets close, but it never touches the y-axis. So the domain is all positive real numbers, everything to the right of the y-axis. The range, of course, though, the y value can be anything. So the y value is the all real numbers. Now here the x-intercept is the point 1, 0. Remember on the other graph, the exponential graph, the y-intercept, we had the y-intercept 0, 1. Well, here we have the x-intercept 1, 0. And of course the graph has no y-intercept. The y-axis is a vertical asymptote. So the y-axis serves as a vertical asymptote. and then f is increasing if a is greater than 1. So notice here, kind of like we had up here, here the a was 5, which is greater than 1, so the function is increasing. And then here the base was 1/4, so a was less than 1, so the function is decreasing. And then of course you can see that if you do the horizontal line test, you can see that the function is 1-to-1 and therefore has an inverse. Okay, so a couple of common functions that we want to talk about are the natural log function. Now, if anytime you see this function, ln(x), it's called the natural log function. And what it is, it's the log function that has base e. And it looks like this. Now, if you have a base 10, you don't have to write the 10, but that function is abbreviated just with log of x without a base given. So if you don't have a base given here, then you know that's the log of x base 10. Okay? And this is just some couple more graphing techniques that you can do. You see that if you wanted to graph minus the natural log of negative x, you know the negative x would reflect the graph about the y-axis, and then the negative one in front of it would then reflect that result about the x-axis. And then here's the common log, so you would take this common log and the x minus 3 would shift that common log to the right 3 units, and then the plus 2 would shift it up 2 units. Now these logs are easy to graph on your calculator because your calculator should have the keys for natural log and common log. So you should have, if you see the log key, it's the base 10 log, and if you see the ln key, it's the base e log. And again, make sure you can calculate values for these logs on your calculator. So if you wanted to, if you had common log of x and you needed to evaluate that function at 235, you just grab your calculator and punch in log of 235 and you get 2.371. And what that means is, of course, is that it tells you what power you raise 10 to get 235. So apparently if you raise 10 to the 2.371 power, you'll get 235, approximately anyway. Alright, and then this one says 3 minus natural log of x, and so if you evaluate that function at 25.03, then you get 3 minus the natural log of 25.03, and do this calculation on your calculator and make sure you can get negative 0.22. So that's basically the concept of logs and exponential functions. And there's one thing while I'm here, I'll go ahead and say this. The log function base e and the exponential function base e are actually inverses of one another. So these two functions, y equal e to the x and y equal the natural log of x, are inverses of one another. And actually any exponential function that has a particular base will be the inverse of the corresponding log value that has the same base. So for example, if this was 2 to the x, then you would have its inverse would be log of x base 2. So that's true. That's the relationship between exponential function and logs.